Okay, so now we're looking at the 1988. So the first time you look at this, you want to have a heart attack because you say, oh, there's a spring inside a spring, and we never did that before. This problem's actually a lot easier than it looks. So, again, we have the mass. So it says a 5 kilogram mass initially slides with a speed v naught, okay, in a hollow frictionless pipe. The end of the pipe contains two springs, the one nested inside the other, as shown above. The object makes contact with the inner spring at point A and moves at 0.1 meters. And you notice there's a graph over here, which we're going to be getting information from the graph to do the problem. So the whole point here is from here to here, it's only the little spring, okay? And then moves an additional 0.05 meters before coming to rest at point C. So now you have the two springs from here to here. The graph shows the magnitude of the force exerted on the object by the springs as a function of the object's distance from point A. Calculate the spring constant for the inner spring. So that's this one. So first of all, we know that we're going to be using Hooke's law. So with Hooke's law says F is equal to minus kx. And remember, the negative sign is because the spring force is opposite the displacement. But in this case, we don't even need to worry about all that. You don't have to worry about the negative sign, or if you want, you can put it in. So the spring constant K, let's just say, is going to be F over X. Well, we know that it's compressed 0.1 meters. But where do we get the force from? Now we look at the graph. So remember the graph, this is point A, this is point B, and this is point C. Okay? So now I'm going to look at my graph and I'm going to say, okay, at 0.1 meter, what's the force? Oh, it's 20. So this is just going to be 20 newtons over 0.1 meter, and this is 200 newtons per meter. So that was actually pretty easy, but we're just using the graph. All right, part B says calculate the, that's supposed to be decrease. Calculate the decrease, which is just the change. Remember, that's just going to be the change. So when you see increase, decrease, that's my change in kinetic energy of the object as it moves from A to B. So we know that the change in the kinetic energy is equal to the work done. Okay? And on a force versus distance graph, we know the work is going to be the area under the curve. So that's the key to this. The area under the curve is the work done. Okay? So now, what is that area under the curve? Well, when you look at your graph, this is the curve, and we want this area. So that's a triangle. So it's going to be 1/2 base times height. So 1/2 of 0.1 meters times 20. That's the height. So when we do this, this comes out to be 1 joule. So this is all about the work energy theorem. That's what they were saying if you knew. All right. Question C. Calculate the additional decrease in kinetic energy as it moves from B to C. So again, we're going to do the same thing. We're going to do delta K is equal to the work, which is the area under the curve. So now we're going from B to C. So if I look at it, sometimes you don't have to say, oh, what's the equation? Sometimes I just make it easy. And I say, oh, here's a rectangle and here's a triangle. Okay? So what I'm going to do when I do this is I said I'm just going to do the rectangle plus the triangle. Keep it easy. So I'm going to say base times height plus 1/2 base times height. So it's going to be 0.05 meters times 20 newtons plus 1/2 of 0.05 times 40. So delta K is going to be 20 divided by 2. By this is just 1. And then that is 1. And 1 plus 1 is 2. And that's my answer. All right. Part D says calculate the initial speed, V naught. Well, speed is going to be in the equation for kinetic energy, which is 1/2 mv squared. So we know the work is equal to the change in kinetic energy. All right. What the key to, and remember, that's going to be what? Kf minus K naught, which would be 1/2 mvf squared minus 1/2 mv naught squared, and we want to solve for V naught. Now the key here is, I know the final velocity is 0 because it's going to be, it comes to rest. Okay, and that's what I pull out of here where it says coming to rest at point C. So when you read a problem, you really have to be careful and say, you know, when I'm reading some of these words, they mean something. So that means this is 0. That whole term goes to 0. Up and to the right means 0, and anything times 0 is 0. Okay. So again, how did I know that? I know the final velocity is 0 at point C because it said it came to rest. All right. So how am I going to do that? So I'm finding the work. So I know that from the 2 plus 1 is 3. That's how much it's going to be. I'm going to add this and this. So remember, work is equal to the change in energy. So it's going to be 3 joules is equal to 1/2 mv naught squared. And now I'll so 3 joules is 1/2 of 5 kilograms times V naught squared. If I want to rearrange that, I can say that V naught is equal to, multiply the 2, so 2 times 3 joules over 5, and then I'll take the square root of all that. So V naught comes out to be 1.09. So the last part, it says calculate the spring constant. This is the part where you're going to have to say, are the springs in series or are they in parallel? Okay. You don't have time to derive the equations. Okay. So in this case, remember that springs are opposite of resistors. If you, maybe you didn't learn about resistors. So here, F total, okay, because they're being added together, is going to be kx1 plus k2x. Okay, because between 10 and 15, between these 2 points, I have both springs together. Okay, so the total force we're going to have, so we're going to have 40 newtons is equal to 200, which I already knew, times 0.05 plus K2 times 0.05. And how did I know that the force was 40? As I look at the graph and it's on a straight line, which means it's linear, okay? And so I had 60 and 20 in between that too. All right, so 40 newtons is equal to 10 plus 0.05 times K2. And then I rearrange this, and I have 30 newtons is equal to 0.05 K2. So K2 is equal to 600 newtons per meter. So with this problem, you're looking at that other graph. But I have a feeling when students looked at that initial picture and they saw a spring inside a spring, they had probably only saw springs that were like in series or parallel, where they're side by side or they're attached together. So that's what made this one the picture. But it wasn't so bad.